Six Sigma in semiconductor equipment manufacturing. In the competitive world of semiconductor equipment manufacturing, achieving near-perfect quality is not a luxury, it's a necessity. This is where Six Sigma plays a critical role. Six Sigma is a disciplined, data-driven approach to eliminate defects and minimize variability in processes. By applying its principles, manufacturers aim to achieve no more than 3.4 defects per million opportunities. That equates to a staggering 99.9996% quality level, often referred to as Six Sigma quality. This level of precision is essential in semiconductor manufacturing, where even a microscopic defect can result in system failure. The methodology drives excellence by systematically identifying root causes and implementing process controls. At its core, Six Sigma transforms quality from a goal into a measurable standard, making data-driven process optimization the foundation of sustainable manufacturing excellence across the semiconductor industry. Understanding the semiconductor industry. The semiconductor industry serves as the backbone of modern technology, with a global market size of $574 billion as of 2023. Each year, more than 1 trillion chips are produced to meet growing demand across sectors. But this scale comes with extraordinary complexity. Manufacturing a chip requires over 700 distinct process steps, features that are just 3 to 5 nanometers wide, and a production timeline stretching from 3 to 4 months. This precision-intensive environment demands rigorous quality controls. Yield requirements exceed 99.99%, with zero tolerance for defects, especially in critical applications like medical devices, aerospace, and advanced computing. Achieving this level of perfection is difficult due to several challenges. These include the need for atomic-level precision, extreme sensitivity to contamination, highly intricate multi-step processes, and the enormous capital costs associated with cutting-edge equipment. Mastering these challenges is essential for delivering the reliability that modern systems demand. Why Six Sigma? The semiconductor industry is uniquely positioned to benefit from Six Sigma due to its extreme quality demands and the intricate nature of its manufacturing processes. Producing chips at nanoscale dimensions, often as small as 3 to 5 nanometers, requires control at an atomic level. With more than 700 individual steps and a production cycle lasting months, there's immense potential for variation, error, and waste. Any small deviation can result in catastrophic failure, especially in high-reliability sectors like aerospace, automotive, or medical devices. That's why Six Sigma is so critical. It brings structured problem-solving, rigorous statistical analysis, and a relentless focus on reducing variation. The goal is not just to fix problems, but to prevent them before they occur. By embedding Six Sigma into semiconductor manufacturing, companies can consistently meet the ultra-high yield expectations of 99.99% or higher, while controlling costs and improving performance reliability. What is Six Sigma? Six Sigma is a data-driven methodology designed to eliminate defects by identifying and reducing variation in manufacturing processes. At its core, Six Sigma focuses on achieving consistency and excellence by addressing the root causes of process issues. The name sigma comes from the Greek letter used to denote standard deviation, a key measure of variation. When a process operates within 6 standard deviations, plus or minus, from the mean, it achieves near-perfect performance with only 3.4 defects per million opportunities. This translates to a 99.99966% quality level. Developed in 1986 at Motorola by engineer Bill Smith, Six Sigma has evolved into a global standard for operational excellence. Its core principles include customer focus, data-driven decision-making, process optimization, and proactive management to prevent defects before they occur. With an impressive 85% success rate, Six Sigma continues to deliver meaningful improvements across industries, especially where precision, consistency, and quality are non-negotiable. Key insight: prevention over inspection. The key insight behind Six Sigma lies in its transformative approach to quality management. Traditional systems often rely on inspection, catching defects after they occur. But in high-stakes industries like semiconductor manufacturing, even a single undetected flaw can compromise product reliability. Six Sigma flips this model by emphasizing prevention over inspection. It focuses on identifying the root causes of variation and addressing them proactively before defects ever occur. This shift is not just philosophical, it's operationally vital. Preventing errors during the 700-plus intricate process steps of semiconductor production is far more effective than detecting them at the end. With feature sizes shrinking to the atomic level, Six Sigma's data-driven, statistically rigorous approach ensures consistent control and continuous improvement. By transforming quality assurance into a proactive strategy, Six Sigma becomes a perfect fit for the precision, complexity, and reliability demanded in semiconductor manufacturing. The DMAIC methodology. DMAIC is a structured five-phase approach used for problem-solving and continuous improvement. The first phase, define, focuses on identifying the problem and setting the project scope. Key activities include drafting the project charter, capturing the voice of the customer, stating the problem clearly, and defining goals. Tools like SIPOC diagrams and process maps help outline inputs, outputs, and stakeholders. Next is measure, where teams develop a data collection plan, establish baseline metrics, assess process capability, and validate measurement systems using tools like control charts and measurement system analysis, MSA. In analyze, teams identify root causes using techniques like the fishbone diagram and Pareto chart, run hypothesis tests, and map processes to discover inefficiencies. The improve phase involves designing solutions, conducting pilot tests, performing risk assessments, and executing changes using tools like design of experiments, DOE, and failure modes and effects analysis, FMEA. Lastly, control ensures lasting results through standard procedures, monitoring plans, and training, supported by tools like statistical process control, SPC, and POCA-YOC. DMAIC projects typically last 3 to 6 months, involve 4 to 8 team members, and deliver a 15 to 25% improvement. The DMAIC methodology. DMAIC stands for define, measure, analyze, improve, and control. A proven, structured methodology used to drive process improvement. It is foundational to Lean Six Sigma and is widely adopted across industries because of its disciplined, data-driven approach. Each phase builds logically on the previous one, helping teams move from identifying a problem to sustaining a long-term solution. What makes DMAIC successful is its emphasis on clearly defining the problem, collecting and validating relevant data, analyzing that data to uncover root causes, developing and testing improvements, and finally ensuring those improvements are maintained. The process reduces guesswork, improves focus, and leads to results that are both measurable and repeatable. The true success factor of DMAIC lies in its systematic approach, which minimizes variability and maximizes efficiency, ultimately driving meaningful change across operations. This methodology enables organizations to solve problems with confidence and deliver consistent, measurable results. Six Sigma applications in semiconductor equipment manufacturing. Six Sigma plays a powerful role in semiconductor equipment manufacturing by driving improvement across 4 key areas: yield, defects, equipment efficiency, and process performance. First, yield improvement focuses on wafer and die optimization, leading to a 15 to 25% increase in yield and up to $2.5 million in annual savings. Techniques such as wafer inspection optimization, tighter control over process parameters, and contamination reduction help achieve these gains. Second, defect reduction supports zero-defect manufacturing with a 90% decrease in defects and a target defect rate of 3.4 parts per million. Success here relies on particle contamination control, improved pattern fidelity, and tighter control of critical dimensions. Third, Equipment efficiency targets 95% overall equipment effectiveness, OEE, and 50% downtime reduction. Key enablers include predictive maintenance to avoid breakdowns, setup time reduction for faster changeovers, and tool matching optimization to ensure consistency. Lastly, process optimization delivers manufacturing excellence by cutting cycle times by 30% while enhancing process capability to Six Sigma standards. This is achieved through statistical process control, robust experimental design, and real-time performance monitoring. Six Sigma applications. Impact highlights. The benefits of Six Sigma in semiconductor equipment manufacturing are not only operational, they are strategic. The methodology consistently delivers measurable business value across key performance areas. One of the most compelling results is over $10 million in annual cost savings, driven by reduced waste, improved yields, and optimized processes. Second, Six Sigma boosts productivity by 25%, empowering teams to work smarter through better process design, tighter control, and fewer defects. This leads to more output without increasing resources. Third, companies adopting Six Sigma achieve up to 40% faster time to market, reducing delays in development and production. With streamlined workflows, better forecasting, and more predictable outcomes, products are delivered more quickly and efficiently. Finally, Six Sigma's focus on quality and consistency leads to 99.7% customer satisfaction. By addressing issues at their root and ensuring stable processes, organizations consistently meet or exceed customer expectations. These metrics reflect how Six Sigma transforms operations into competitive advantage. Benefits and outcomes. Measurable impact of Six Sigma implementation. The measurable outcomes of Six Sigma implementation are both financially and operationally significant. On the financial side, Six Sigma leads to a 20 to 30% reduction in manufacturing costs, translating to over $5 million in annual savings per fab. These savings are driven by a reduction in scrap and rework, minimized downtime due to improved equipment reliability, and better resource utilization across processes. Beyond cost savings, Six Sigma significantly boosts quality excellence. It enables organizations to achieve a 99.9% product quality rate, a near-perfect standard that enhances brand reputation and customer trust. Additionally, it achieves up to 90% defect reduction, which means fewer returns, lower warranty claims, and greater reliability in the field. These results are made possible through enhanced process capability, consistent adherence to product specifications, and a strong focus on customer satisfaction. The cumulative effect of these benefits results in a 400% average return on investment, ROI, making Six Sigma not just a quality initiative, but a strategic business advantage. Benefits and outcomes. Implementing Six Sigma delivers measurable improvements in both operational efficiency and business growth. One of the most impactful results is a 40% reduction in cycle time. This improvement is driven by streamlined workflows that eliminate unnecessary steps, reduce setup times, and minimize waste. These changes also support predictive maintenance strategies, which help prevent unplanned downtime and extend equipment life. As a result, equipment overall effectiveness, or OEE, can reach 95%, representing highly optimized performance across availability, performance, and quality metrics. On the business side, Six Sigma enhances strategic growth by accelerating time to market by 60%. This speed leads to improved market competitiveness and strengthens brand reputation. Furthermore, companies experience exceptional customer retention, up to 98%, thanks to consistent quality and reliability. Collectively, these gains yield a remarkable 400% average return on investment, making Six Sigma a powerful driver of sustainable business success. Transformation impact, before versus after Six Sigma. Six Sigma delivers transformative improvements across key performance indicators by systematically reducing variation and defects. One of the most dramatic changes is in defect rate, which drops from 15,000 parts per million to just 3.4 ppm. This staggering reduction directly contributes to higher quality and reliability in products and services. Alongside this, the yield rate improves significantly, from 65% to 90%, indicating a much higher percentage of acceptable units being produced without rework or scrap. Process capability also sees a massive leap, moving from 2.5 sigma to a full 6 sigma level. This change reflects a tighter, more consistent production process with far fewer deviations. Finally, customer satisfaction rises from 70% to an impressive 98%. This boost results from improved quality, more reliable delivery, and fewer issues reaching the customer, highlighting how Six Sigma fosters excellence from manufacturing to market. Implementation challenges and solutions. Successfully deploying Six Sigma often involves overcoming two major categories of barriers: cultural and knowledge-based. A high-impact challenge is resistance to change. This includes employee skepticism, fears about job displacement, and comfort with the status quo. Additionally, management may hesitate to fully buy into the transformation. These cultural barriers can stall progress unless effectively addressed. The proven solution is strong change management, which yields very high effectiveness. Key actions include securing executive sponsorship, launching clear communication campaigns, involving employees early, and celebrating wins to reinforce momentum. Another significant challenge is the training and skills gap, which has a medium impact. Many employees may lack statistical knowledge, be unfamiliar with the DMAG methodology, or need help mastering data analysis and Six Sigma tools. A comprehensive training approach addresses this. Belt certification programs, hands-on workshops, mentoring, and continuous learning initiatives all support skill development and drive long-term success. Implementation challenges and solutions. Part 2. Another major challenge in Six Sigma deployment is resource constraints, classified as investment barriers. These include high initial investment costs, limited time allocation, and the need for dedicated personnel. In many cases, existing technology infrastructure may not be sufficient to support process improvements. The impact level of this barrier is high, often causing hesitation or delay in project rollout. To overcome this, a phased implementation strategy proves highly effective. Phased implementation involves starting with pilot projects that allow organizations to demonstrate quick wins. These early successes can build confidence and stakeholder support. As a result, teams can gradually scale up efforts with reduced financial and operational risk. This approach enables resource optimization and better planning. Ultimately, it helps to mitigate risk, maximize impact, and align teams around realistic expectations, setting a solid foundation for long-term, data-driven improvement and customer-focused outcomes. Real-world case studies. Six Sigma has delivered massive results in the semiconductor industry, as illustrated by the successes of Intel Corporation and Taiwan Semiconductor Manufacturing Company. Intel, recognized as an industry leader, achieved a 75% defect reduction and saved $2.1 billion annually through its global fab optimization program. By implementing the DMAIC methodology across 15 fabs worldwide, Intel reduced process variation by 60%. This effort enabled the company to reach Six Sigma quality in critical processes, contributing to a 95% improvement in yield. Taiwan Semiconductor, a global foundry leader, achieved an extraordinary 99.5% first-pass yield in its advanced node manufacturing. By optimizing 7 nanometer and 5 nanometer processes, TSMC accomplished zero-defect manufacturing. Their results include $1.8 billion in cost avoidance and an impressive 85% reduction in cycle time. Furthermore, customer satisfaction reached an outstanding 99.8%. Together, industry-wide Six Sigma initiatives have driven over $50 billion in cumulative savings, clearly proving their value and impact. Real-world case studies. In the semiconductor manufacturing sector, real-world results speak volumes. Samsung Semiconductor, recognized as a memory and logic leader, embarked on a 6 Sigma quality journey and has currently achieved a 4.2 Sigma level. Their efforts have yielded a remarkable $3.2 billion in return on investment. They also achieved an impressive 92% in overall equipment effectiveness, a key metric in manufacturing excellence. This success was driven by dynamic random access memory and NAND flash optimization, the strategic deployment of predictive maintenance systems, and implementation of global standards to unify quality and performance across facilities. Meanwhile, Micron Technology, known for its memory innovation, has made groundbreaking strides in sustainable manufacturing. With a 68% reduction in waste, $850 million in efficiency gains, and a 97% quality score, their achievements are powered by a 3D NAND process breakthrough, adoption of sustainable practices, and AI-driven quality control. Together, these case studies represent over $50 billion in industry savings. Collective industry impact. The collective impact of real-world semiconductor improvement projects is both measurable and remarkable. Over 500 projects have been successfully completed, directly contributing to $8.2 billion in total savings across the industry. These savings represent more than just cost reduction. They reflect smarter processes, reduced material waste, improved tool utilization, and faster cycle times. One of the most impressive metrics is an average defect reduction of 85%, indicating that the projects have significantly improved product quality and consistency. This has driven an extraordinary average return on investment of 450%, demonstrating the strategic value of operational excellence initiatives. Perhaps most impressively, customer satisfaction rates have reached 99.7%, a strong indication that the improvements made are not just internally efficient, but also deliver results that customers notice and appreciate. This level of performance sets a new benchmark in global semiconductor manufacturing. Future trends and technologies. Between 2025 and 2030, next-generation Six Sigma strategies in semiconductor manufacturing will be driven by 3 major innovation pillars: AI integration, Industry 4.0, and predictive analytics. AI integration, currently in the emerging stage, focuses on machine learning and deep analytics. This includes predictive defect detection to prevent issues before they arise, automated root cause analysis to accelerate troubleshooting, and self-optimizing processes that adapt in real time for improved outcomes. Industry 4.0 is accelerating rapidly with IoT and connected manufacturing. Real-time sensor networks enhance data visibility. Digital twin technology allows for virtual modeling of production environments, and edge computing brings powerful analytics to the factory floor. Lastly, predictive analytics, now in a mature stage, is already widely used. It enables equipment failure prediction, advanced yield optimization models, and accurate quality forecasting. These technologies together set the stage for smarter, faster, and more resilient semiconductor manufacturing. Future trends and technologies, Part 2. The second wave of next-generation Six Sigma innovation highlights emerging technologies that are reshaping quality and process control from 2025 to 2030. Smart automation is expanding rapidly, leveraging autonomous quality control solutions. Automated inspection systems detect issues in real time, self-correcting processes minimize human intervention, and robotic process automation ensures precision and consistency. Cloud analytics, labeled as critical, plays a pivotal role in scalable data processing. With real-time global dashboards, organizations gain visibility across sites. Cross-facility benchmarking promotes performance comparisons, while collaborative improvement fosters shared learning and rapid issue resolution. Looking further ahead, quantum computing represents the future frontier. Though still in the research phase, it promises ultra-complex optimization capabilities. Potential applications include molecular-level simulation for material innovation and advanced pattern recognition for highly complex data sets. Together, these innovations aim to elevate semiconductor manufacturing to unprecedented levels of intelligence, speed, and precision. Future trends and technologies. Impact goals by 2030. By 2030, next-generation Six Sigma practices in semiconductor manufacturing are expected to drive transformative improvements across key operational metrics. One of the most ambitious targets is a 300% efficiency gain, achieved through automation, advanced analytics, and continuous process optimization. This will significantly enhance throughput and reduce bottlenecks across the fab floor. Alongside this, the industry aims to reach a Six Sigma Plus quality target of 99.9%, minimizing defects and ensuring near-perfect product consistency. These advancements are complemented by a projected 50% reduction in costs, primarily driven by AI technologies that optimize resources, predict failures, and streamline production. Finally, 24/7 autonomous monitoring will become a cornerstone of operational excellence, enabling real-time detection and correction of anomalies without human intervention. These goals reflect a future where semiconductor manufacturing is faster, smarter, leaner, and more resilient, setting new global standards for precision and performance.